All right, everybody, the time has finally arrived to prove R equals T in the minimal case. After all this time, after all these months, we will finish the proof today, which will finish the proof of R equals T in general, because we've already done the general case assuming the minimal case. So let's do it. Let's recall the theorem. So see video 11.2 to recall any notation and setup involved here that I don't cover in more detail. Okay. So the setup is we'll fix a continuous representation, rho bar, from the Galois group of Q to GL2 of K, where K is some finite field of characteristic sum prime L. We'll assume that L is odd, that rho bar is irreducible, that the restriction of rho bar to the Galois group at L is flat or ordinary, that rho bar has cyclotomic determinant, and that rho bar has square-free conductor. Okay. For such a representation rho bar, we'll define sigma sub rho bar to be the set of primes P, such that either P is L and rho bar restricted to the Galois group at L is good and ordinary, or P isn't L and rho bar is unramified at P. Again, there's this like at L, good replaces unramified kind of idea going on here. So here's the theorem, R equals T. It says for all finite sets of primes sigma and sigma sub rho bar, the surjective ring homomorphism phi sigma from the universal type sigma deformation ring R sigma to the universal type sigma Hecke algebra T sub sigma is actually an isomorphism of complete intersection rings. Okay, so we've already proven this in the general case where sigma is anything, but we had to assume the so-called minimal case where sigma is the empty set. We're now prepared to prove this theorem in the case where sigma is the empty set. We're just going to begin by recalling all the needed results from the chapter. Okay, again, I'm not going to recall all the notation from this whole chapter in this video. It's a straightforward check to begin the proof that you can extend scalars, and so you can assume the following. First, you can assume the eigenvalues of all elements in the image of rho bar are actually K rational. And then you can also assume that there's a new form F. It's like a type empty set modular deformation of rho bar with coefficients that are in O. This gives me an O algebra homomorphism T empty set to O, because these are equivalent statements here. The fact that you can assume that this new form exists was essentially covered in chapter 7. Okay, so we actually have a type empty set modular deformation, so this is like not an empty ring or something. Okay, so let's recall all the results we need. So lemma AI from this chapter said the following. It said let L be Q adjoined square root of -1 to the L minus 1 over 2 all times L. Then rho bar restricted to the Galois group of L is absolutely irreducible. We also had proposition 4, which said that if L is this field here, suppose that rho bar when restricted to GL is absolutely irreducible, which this lemma guarantees. Then there exists, so this was the magic R we called it, there exists a magic non-negative integer R, such that for any natural number n, there is a finite set of primes Q sub n, so depending on n, such that 4 things are true. First, if Q is a prime in Q sub n, then Q is 1 mod L to the n. Second, if Q is in Q sub n, then rho bar is unramified at Q, and rho bar of Frobenius at Q has distinct eigenvalues. 3, and this is kind of a big one, the cardinality of Qn is always R. And then 4, R sub Q sub n, so the type Q sub n deformation ring, the universal type Q sub n deformation ring, can be topologically generated by R elements as an O algebra. Okay, so we're just recalling results. Let's also recall some more results while we're at it. So proposition 3, the natural map from RQ to R empty set, so this natural surjection here, actually admits an isomorphism whose kernel is just the the type Q augmentation ideal. Okay, in other words, RQ mod AQ is just isomorphic to R empty set. We had proposition 5, which said let Q be a finite set of primes with the usual properties. Then the type Q universal Hecke algebra is a free O bracket delta Q module, where this module structure is inherited from the structure on RQ via the map phi Q, the R equals T map, in other words, from RQ to TQ. And then kind of what we really need from this is, so the corollary AQ, we called it, a consequence of this is that T empty set is actually isomorphic to TQ mod AQ, if Q is a finite set of primes with the properties from above. Okay. We're also going to need a criterion for isomorphisms of complete intersections that we covered a couple of chapters ago. We'll call it criterion 2. It says the following. Suppose that for each integer m positive, we have a commutative diagram of O algebras as follows. So O double bracket S1 through Sn should map to, let's call it Rm, should map to Tm via a map phi sub m, and then Rm should map to R from R equals T, and Tm should map to T from R equals T, and And then we have our R equals T surjection phi going from R to T. So suppose we have this for each M, such that there's actually a surjection of O algebras from O double bracket x1 through xn onto Rm. So there's like another up here. I always think of it as like O double bracket x1 to xn surjecting onto Rm. Okay. And then suppose also that these vertical arrows here induce isomorphisms between R and Rm mod J0 Rm and T and Tm mod J0 Tm. Okay, so I didn't write it here, but let me write it in. So Jm is the ideal in O double bracket S1 through Sn generated by omega m of S1 through omega m of Sn, where omega m of S is the polynomial 1 plus S to the p to the m minus 1, okay? Maybe, I guess, in this case, it would be L, because we're using L instead of P. Okay. Okay, so we have that. So suppose these vertical maps basically induce isomorphisms with kernel J0. Okay. And then also suppose that Tm mod Jm is finite flat over O double bracket S1 through Sn mod Jm. Then this map, phi from R to T, is an isomorphism of complete intersection rings over O. Okay, so we've already covered all this. So let's get back to the proof. I think we have all the results that we need now to finish. So let's do it. By lemma AI in proposition 3, we can find a magic R non-negative such that for each natural number n, there exists a set Q sub n of R primes that are all 1 mod L to the n, and such that if Q is in Q sub n, rho bar is unramified at Q, and rho bar of Frobenius at Q has distinct eigenvalues, and that the type Q sub n universal deformation ring can be topologically generated by R elements as an O algebra. Let's continue. Let's set Jn prime to be the ideal generated by all of the Si plus 1 to the L to the n sub I minus 1 powers. This is an ideal in O double bracket S1 through Sr. What are these Ni's? They've been chosen so that O double bracket S1 through Sr mod J prime n is isomorphic to O bracket delta sub Q sub n. That this is possible was discussed in video 12.3. Okay? Well, then for each n, we have the following commutative diagram. This should look pretty familiar. We go from O double bracket x1 through xr to R sub Q sub n. We also have a map from O double bracket S1 through SR to R sub Q sub n. Okay. Then we have a natural surjection from R sub Q sub n to T sub Q sub n. We've known this for a while. We also have the R equals T empty set map, phi sub empty set, from R empty set surjecting onto T empty set. And then we have maps from R Q sub n to R empty set and T Q sub n to T empty set. Okay. Where are we getting this left surjection from here? This is from chapter 11. We talked about this. Okay. And then where are we getting this top map from? Well, remember, RQN is an O bracket delta Q algebra, but O bracket delta sub Q sub n is isomorphic to a quotient of this guy. So that's why this map exists. Okay, and then these maps we've already known about for a while, right? So we have all these maps. Let's continue. We have the following facts now. If you take RQN and mod out by the ideal generated by S1 through SR, that is isomorphic to our empty set by proposition 3 using the description of the augmentation ideal A sub Q from video 12.3. We also know that T sub Q sub n is finite and free over O double bracket S1 through SR mod J prime n by proposition 5. And we finally know that T sub Q sub n mod the ideal generated by S1 through SR is isomorphic to T sub empty set by corollary A sub Q. Okay, well, I think these just check off all the boxes we need to use criterion 2 and be done, right? If you let Jn be, like I said, the ideal generated by Si plus 1 to the L to the n minus 1, where I runs from 1 to R, and you replace T sub Q sub n and R sub Q sub n by T sub Q sub n mod J sub n and R sub Q sub n mod J sub n, this gives us a Jn structure as per criterion 2. It gives us those commutative diagrams that we were after. We call those Jn structures back in chapter 10. Okay, so I don't know, guys. Criterion 2 just applies then to the case sigma equals empty set and guarantees us that phi sub empty set from R empty set to T empty set is an isomorphism of complete intersection rings, and that does it. So we're all done with R equals T, which is the crux of the proof of modularity. All we have to do now is fill in some holes about the flat deformation functor that we used throughout the previous chapter or two, and we should actually be done with the proof of FLT. Modulo some other things I want to talk about, like Carriol's theorem and Mazur's theorems and stuff like that. So it's been an incredible journey up till this point. Thank you all for watching, and I'll see you in the next one.